What is up, team? It's your boy, the Canologist, and I'm back to do path sum. Alright, let's do this question. Given the root of a binary tree and an integer target sum, return true if the tree has a root to leaf path such that adding up all the values along the path equals the target sum. A leaf node is a node with no children. Okay. So what I'm going to do here is first I'm going to check the constraints. Number of nodes in the tree can be 0. If there are no nodes in the tree, do I want to return true or false? Okay, so return true. Okay, so this is a truthy falsy question, right? So my base case, if root, right? If the root is let's see. If the root is equal to none, return false. This is an auto false condition because if you have no root, you have no target sum, right? So that's automatically false. What else do I want to do? I'm going to create a variable. I'm going to define a function actually. Because it's recursive, I want some sort of running total. We did a question before this. I don't know if it's in the problem list. Minimum depth of the array. So the concept of this question will be sort of similar. So let's go to the whiteboard. 1, 2, 3, 4, 5, 6, 7, 1. Okay, let's do that. Let's do this one. This one. So 1, 2, 3, 4, 5, 6. Okay. And this is an X for null. This is an X for null. Okay, so basically what I want to do here is I want to traverse this array and accumulate a total. Well, not array, this tree. So let's say T question mark starts at 0 here, whatever the value of this is. So basically if my null value, if my root node is null, then I get false. Right? If there are nodes, I can keep adding it to this accumulated total. So go up here, then I check left and right node, alright? And then I go add that total to here, to here, to here. So basically what I did in the previous problem was it traverses to see if you can find the leaf node and find out the shortest path. This time we don't care. So the last question we cared about the nodes, not the value. This time we don't care about the nodes, we care about the value. So we have to figure out a way to pass on that value recursively. So this is like the thought process you have to have when you're doing a recursive type of function. Am I looking for values? Am I looking for nodes? Am I looking for both values and nodes? In this case, path sum is a true false. So it's just looking for a value and whether you should return true or false. So without further ado, we will take this to the next level. which is leaf nodes node with no children, -1,000 node value, target sum could be between -1,000 and 1,000. Node value could be between -1,000 and 1,000. Okay. Given the root of a binary tree, determine if a tree has a root to leaf path. A root to leaf path. So what I'm trying to do is create a function called root to leaf. Root to leaf total. So root to leaf tot is going to be what I call it. It's defined within the function, so I have to give it a self condition. Obviously give it a node. Then I'm going to give it the total. My total is going to be 0. I pass in the target sum. I'm going to pass in the target. My total equal to 0. My total will be the root node value. So I'll just pass in total as is. Because if there's no root, I just return false. And then here, I want to link it to this to final equals self dot root to leaf total. The reason why we create these functions within itself is because when you deal with something recursively, you need a way to track your memory, or you need a way to track value, right? Because as you keep recursing on that call stack, the call stack only remembers the command it's executing. So let's say you save 3, when you run that same function again, it's fresh. You don't remember that 3. You have to have a way to pass up that value. So what I do is I create an auxiliary function here, and I add an extra value called total, so I can keep track of it as it goes through recursions. So once it goes 3, then it runs the function again. It keeps that value of 3. Now we can manipulate it and return it back when we're done recursing. So when you hit your base case and you return, this total value is manipulated for every single recursion up until that return. That's why we do this. There's obviously other ways to do it. It's just that I found that this is the most, it's the simplest way I can do it, or the way I understand it. If there's a better, more sophisticated way, I would love for anyone to suggest that to me, or teach it to me, or link a blog or something to me. But this is the way I found that works the best. So I go root to leaf self. So I pass in the root, obviously. I pass in the target sum. So that's what we want to keep track of. And then total. Total. And the total is going to be the root dot value. Because if there is a root, so if there's no root, we return false. If there is a root, we start here. All right. So first things first, I want to check if we're at a leaf node. So our condition to end is to check the leaf node. So we're going to end up doing the comparison. The other way you could do this function is you could just add the total here and just call it within itself. But I just find this way is a bit cleaner. So now I can just return final. But I'm basically doing everything I'm doing here again, because I'm just comparing. But I like the way it's just clean here, and I can put the logic of my function somewhere else, so that way I can modify it if you have a requirement that changes later. You didn't affect your main code, you just changed what's in the function, or you can modify it. This gives you power over your design in a way. Let's see, we're at 11 minutes. Okay. So let's first, we have to identify a leaf node. So our base case to return will be if node.left and node.right. So if node.left equals none, and node.right equals none, return target equals total. So basically, if it's true, return true. If it's false, yeah, return that false. So you return whatever this true or false value is. So that's my base case. Then I want to check my left and right subtrees to see if I hit a base case scenario. So all I'm going to do here is if node.left. So first I'm going to go do an OR condition for the trees. So I'm going to go left subtree. I'm going to make it default false. And it's only going to return true if it matches the condition. So right subtree equals false, and then we do an OR condition. So at the very end, I'm going to do a base return of OR. Over right subtree, because all I care about is the true or false, right? So if I look at node.left, node.right, if those are both equal to none, that means I've hit a leaf node, and I want to add that value at the end. So I'm going to add the target. So I'm going to add node dot this is the what's the tree node object is being defined as. So node val, node left, left, right, and val. So self.val. So I'm going to say node.val. I'll put in brackets. If that's equal to target, return that, right? So I'm going to go if node left, if node dot left. So then I want to explore that subtree. So it's going to be root to leaf. Okay, I don't have to do this. Okay, so I could just leave it as normal. Because I'm going to do that addition here. So root to leaf, node. Then I can go, this will be node.left because I'm traversing. Target. So if it's passing the target value, and then total plus node.left dot value. Make it nice and clear. Node.left dot value, right? And then I'm gonna put that in left subtree. So I'm checking my left subtree to see if there's a leaf node that matches this. I'm gonna check my right subtree for the same thing. So all I gotta do is this next. Control C. Now we just go node right. Go to the right subtree. Root to leaf, node dot right, and node dot right. So basically, what I'm trying to do now is basically what I did here. This minimum path. I'm traversing the subtrees, but this time I'm traversing the subtrees with the intention of figuring out whether my total value that I'm accumulating from a root to leaf node path. So last question was minimum depth of a binary tree. So you have to find a leaf node. Oh fuck. Yep, so I'm back. So basically what you have to do with this, with path sum or minimum depth of a binary tree, was you have to find a leaf node. Here we're doing the same thing. You also have to find a leaf node, but this time we have to make sure that this target value we're given matches the accumulated value up to a leaf node. So basically what's happening with this function is I have two left and right subtree values, which are both false. That way I can return either true or false to my final value up here, which is going to be returned. So for each iteration, it's going to check, okay, let's say I start at 5 and check the left subtree. Right? Is there a node dot left? So node dot left is 4. Okay, so 5 plus 4 is 9. Is there a right subtree? No. So I skip right to return left or right subtree, right? So that'll return back to 4. So the value here is 9 again. Because okay, wait, so let's start again. So 5, I go in here, node dot left is 4, add this, okay, and then it's going to call it again. It's going to call it again for as far as you can go to the left, right? So it's going to be 5, 4, 11, 7. That gets returned here. Does that match the target value? Because now I reach a leaf node where left and right are none. So I keep calling node dot left till I hit 7, because this is going to keep going. Right? It checks my node dot left subtree. 7 doesn't. Okay, so now it comes back up. The call before this, 11 and 2 now Now it goes to the right subtree for that one. And then it returns right or left back. So now we get to no.none equals thing. Right subtree is false. So basically we're checking that whole left subtree for this. The same thing happens on the right subtree now. So now we go to the right subtree. So right subtree, boom, boom, boom. None of these work. Come back here, nothing. That doesn't work. We come back here, nothing. To 13. So basically we keep traversing until we find our left and right node being none. And then it will give us true or false whether a value in the left subtree or the right subtree path equals the target value. And if it doesn't, then it returns both false. So this OR condition will return, this is what gets returned back here, right? This, all this stuff here is what gets sent to this base case. That's checked. So if it checks if the target's equal to the total. So at the end of this, if there's anything that's true in this or this, it'll be compared against the other subtree, and since it's an OR condition, only one of it has to be true. Otherwise, it'll send false in all scenarios. So let's give it a run. Error rendering component. What did I do wrong here? Test case. I don't want to lose the code I wrote, so I'm going to copy all this. Let me refresh. Return subtree final. Okay, let's run my code. Okay, so tree node has no object of value. Okay, that's why. It's root.val. And then here it's going to be root.val, because if you go up to here, there's no value component. It's called val. So I'm going to delete that too. Let's try now. Left subtree. Root to leaf is not defined. Okay, so root to leaf is not defined. That's because it's defined within the function. So I have to call self on itself. So it's going to be self dot root to leaf, the same way I did here. Because it's not an external function. If I defined it outside, I wouldn't have to use self at all. So I could now try this. Left subtree, solution has no attribute, root to leaf, root to leaf tot. Oh, tot. See, look, like half of this, half the errors you can get rid of just by understanding your compiler dialogue. It basically teaches you how to correct your code. And as we saw here, it all works. Let's try submitting it. And what do you know? It beats 96.95% of these solutions. So all we did in this question is build upon the last question. So what I said here is if you go to my previous video, minimum depth of a binary tree, you have to think recursively. Okay, what's my goal? Okay, so one of the biggest goals here for this, and in that last question, minimum depth of a binary tree, you have to find a leaf node. If you have to find a leaf node, that means your base case of your recursion has to look for a leaf node. So if you look here in the code, it says node.left equals none, node.right equals none. So it's telling you, okay, I've found a leaf node. What do I do when I find a leaf node now? Now it's asking me for not a value, but it's asking me to return whether that value matches the target or not. So true or false. So that's why I pass in my target value from the original function target sum as target. And then I go to node and I have my total that's passed on through the recursions. And it compares that. So it will either return true or false. Then, right, because this tree is so huge, right? You can't tell how big it is, right? Because if we look at the conditions of this, you could have up to 5,000 nodes, right? So this is like a small scale tree. Imagine a big scale tree, right? You have to plan your recursive function for something you wouldn't be able to look at, but you know the theory will carry on, right? So this is my base case. Doesn't matter how big this is. If node.left and node.right are none, I know it's a leaf node always, right? So that gives me my root to leaf path base case. So this base case, when you think about something recursively, is what determines whether your recursion ends or doesn't end, and that result. So all this does is this determines when your recursion ends. This return here determines what goes back to your function as the final answer, right? It's because final, this value here, self.root, this is the return that gives you that final answer. This base case is what gets compared in this final answer. I need you to be really, really aware of this when you're writing your recursive functions. What is being returned and what is my base case? What is being returned to the main function? What is my base case? What is being returned to the main function? I'm going to say that again. So now that we know that we have our base case, we have to figure out if the root to leaf path matches. So now we have a recursion for node.left and a recursion for node.right. So when I go left and right, I'm calling itself here, but I have a return value. So it's going to keep calling itself within here. So it's going to go 5. Left.subtree. I'm basically starting from scratch with all the values I gave. So node.left, this is going to be 5 plus 4. Or it's going to be 4. Whatever the fuck. Right? So it's going to be, I passed in 5, and then node plus 5. So it's going to be 5 plus 4, 9. And it's going to start again because it calls itself. Tree is equal to this. So 5 plus 4 is 9. Now it goes again. It's not a leaf node. So now it calls itself again on 11. Boom. 5 plus 4 plus 11. Now it calls itself again. Now we get to 7. Right? So now we're at a leaf node. So this is going to return false into left subtree. Right? And then the next thing it's going to do at the end is go to right subtree. So it's going to return left, false into left subtree. Now we go back to 11. So it keeps going. So the way recursion works is it keeps calling itself until you hit a base case. Okay, so now we hit the base case, that's 7. Now we go back to the previous call because the base case is met. Now we have a return left as false. So now we go back to our 11 call. So 5, 4, 11. And then we go to this right subtree now. Now it's going to call it, boom. It's going to call this on 2. Yes, this is a leaf node. So now it's going to go left to right subtree. Now we have our left to right subtree filled. And now it's going to compare this. Left or right is their path. And if that path is true, it returns back to here. Boom. And final. So that is how you solve that question. So if you like this video, please give it a thumbs up. Please put your feedback, remarks, anything you'd like to see in the comments. I read every single comment. And yeah, I also have a bunch of other videos. Like I said, this problem was built upon the logic from the last problem I solved. So definitely watch through all these problems. I go through the theory on the whiteboard. I go through my thought process throughout this whole thing. And hopefully there's insights that you can draw from there and maybe figure out your own way of solving the problem in the future, right? Maybe you might have a better solution than what I showed you, right? So it all goes back to repetition, doing more problems every day, and just adding the most value you can add, and you get better over time. I'm getting better over time, right? I couldn't solve the last question. I could solve this easy, right? So It's only a matter of time. All right. Well, with that being said, I am gonna end this. Knologist is out.